Ladies and gentlemen, welcome to the second part from the geometry lecture from Math 4000, problem solving for Putnam. Well, I decided to do a continuation of the previous lecture since I didn't have time to cover vector geometry, and probably I'll do another one where I should cover something about complex numbers in geometry and a little bit of conics. Anyway, but first, before I even go and talk about vector geometry, I would like to continue with some of the problems that I didn't have a chance to cover them in the previous lecture, and I think I'm going to start with that. Those problems are like basic geometry, Euclidean geometry, and remember last time we did this problem with the maximum value. Well, another problem, so that was problem number 2, but let me see now problem number 3. So problem 3, which is a Putnam Putnam A2 and 2004, I think, yes. And the statement says the following: for I from 1 equals 1 and 2, let Ti be a triangle. As you can see, I have 2 triangles here, T1 and T2. So Ti be a triangle with side lengths AI, BI, CI, right? And area AI. Okay, suppose that A1 is less than A2, B1 is less than B2, and C1, as you can imagine, less or equal than C2. So we have an order between the lengths of the side lengths of the 2 triangles, and that the second one, the second triangle T2, right? The second triangle is acute. All right. So we assume this. Okay. Well, the question is, does it follow that the areas, the area of the first triangle is less or equal than the area of the second? That is the question, and I want you to look at it. It's a very important. Well, it was an A2 problem. Well, let's analyze a bit the problem. The problem is not hard, it's very easy, but we need to look very carefully at it. It as just a small trick, I would say. So let's see, we have the 2 triangles. Let's say this is triangle 1. In fact, we don't even need a picture, but anyway, so this is T1. Let's say this is A1, B1, C1. And we have here the triangle 2. So this is T2. So this A2, B2, C2. And we know that A1 is less than A2 and so on. But also I know that this, the second one is acute angle triangle. So this means that each angle is less than 90 degrees. Okay. All right, let's analyze it a bit. So let's denote the angles in some way. Let's say that the angles are, this is, let's say alpha 1, alpha 2, in fact, alpha 1, beta 1. Okay, let me put it this way so that I don't need to have alpha 1, beta 1, and gamma 1. And here I'll have alpha 2, beta 2, and gamma 2. So these are the angles of the 2 triangles. Okay, and we have to analyze something here. So I know that I have an information about the second triangle. If you look at it, it says it's acute, right? So what does this mean? Let's analyze this. This means that, well, we need to get some information about these angles. And now the trick is the following. So since let's say the two sets of angles have the same sum, right? In other words, the sum of, okay, so alpha I plus beta I plus gamma I is pi with alpha 1 and 2, or alpha for I 1 and 2. All right, so this, since we have this, well, what does this mean? This means that there will be an angle, right, from the triangle, from the second triangle. It follows that there is an angle from the from T2, let's say, right, from the second triangle, which is larger than its corresponding angle on the first triangle. On T1. Okay, so we know this. Well, well, we can, without loss of generality, we can place these two triangles on the x-axis, and with this angle at the origin, and the b sides along the x-axis. So let's do that. So without loss of generality, suppose that alpha 2 is greater or equal than alpha 1, let's say, right? Okay, and we can place T1 and T2 on the, let's place them okay, let me be more specific here. Let's place T1 and T2 with this angle right at the origin, and the b sides, let's say, on the x-axis. Okay, all right. Now we take the b sides to be the basis of the triangles, and then the heights. So now take the b sides to be the basis of T1 and T2. Right? Okay. So once we do this, now we can express the heights. Well, the heights then we know that the heights can be expressed, let's say, or the altitudes can be, these are C I times sine of alpha I, right? With I 1 and taking values 1 and 2. And we know that, so let me be clear, H1 will be C1 times sine of alpha 1, and H2 will be C2 times sine of alpha 2, right? Well, we know that C1 is less or equal than C2. We know that alpha 1 is less or equal than alpha 2, right? Sine will be increasing, so from here it will follow easily that H1 will be less or equal than H2. Well, guess what now? We're basically done. The only ingredient that's missing now, it's just the area. Now the areas of T1 and T2 are given by let's call this area of T1, which will be nothing else than just 1/2 times the base B, let's say B2 times H2. But, oh, sorry, this is T1. So B1 times H1, which will be less or equal, since we have this inequality here, and we already knew the inequalities between the side lengths of the two triangles. This will be less or equal than 1/2 times B2 times H2, which is nothing else than just the area of the triangle T2. Well, now, is this true? The answer is yes. And that's the proof of it. That's the problem. Anyway, this was an easy problem, quite easy, I would say, for a Putnam, but and this goes back in 2004. You will see that there are a bunch of easy geometry problems. Well, not so many these days. They're a little bit more difficult. But now let me draw your attention with another problem. And this was problem number 4. This was a Putnam B1 in the year 1999. And the problem has the following statement. Right angle, or maybe right triangle, let me say it explicitly. The right triangle ABC has a right angle C. Okay. And let's denote this, the angle, the measure of the angle BAC to be theta. And now let's say the point D is chosen on AB such that AC, the segment AC is the same as AD, and it's, so both of them are equal to 1. And now we're going to choose another point. The point E is chosen in such a way, is chosen on BC, so that the angle CDE is also theta. Okay. And now the perpendicular to BC at E meets AB at F. Okay. Now we're asked to evaluate the limit as theta goes to 0 of EF. Wow. So when I put EF in, this means that is the length of the line segment EF. All right, let's look at the statement. Well, I think we should draw a picture so that everything becomes clear. I think the problem will be quite clear when we draw a picture. So let's see, we have a right angle triangle at C. Oh my, let's draw it carefully. Okay, so this is A, B, C. So this is a right angle at C. And now BAC, the angle BAC has measured theta. So this is my angle theta. Okay, and now the point D is chosen on AB, right? So this point D is chosen on AB such that AC is the same as AD. So AC is the same as AD. So these are equal, AC and AD, okay? And moreover, they're equal to 1. Point E is chosen on BC, okay, such that the angle, so E, such that the angle CDE is again theta. So this is my point E here. So CDE, this angle here is again theta. Okay, great. And now we have this point, okay, the perpendicular to BC at E, right, meets AB at F. Okay, so we draw the perpendicular. So this will be F here. So this will be perpendicular. Okay, so this is the picture. I want you to look at it. You'll understand everything that's. And now we're interested in finding, we have to take care of this line segment here, EF. That's what we care about. So the question is, what happens to this guy? So we need to look around here. Well, this is more like angle chasing or something like this. And now let's look around. Let's look at this triangle. Well, let's keep in mind that this is 1 and 1 here. And now let me look at these two angles here. This one is the same as this one, right? This is an isosceles triangle. So let's look at them. And moreover, these are, both of them are, let's see. So we have that, all right. So let's look at, so consider the triangle. And I'm going to consider triangle ACD. And I know that AC is the same as AD, and these are 1. And I know that that guy is theta. But on the other hand, if you look at this, the angle ACB is 90 degrees. So that angle there, it follows that by just looking at some angle chasing. Basically, you don't need to do any chasing. It's quite obvious. It follows that the angles, let's say, the measure of the angle ACD, well, since it's isosceles, is the same as the measure of the angle ADC, and this is nothing else. We know that the measure of the angle ACB is 90 degrees, so it will be, both of them will be equal to 90 degrees minus theta over 2. That, right? Because these two angles plus theta will be, so which are equal, will be give you 180, and then you can write them in this way. So this implies that, so let's see. So we know that these are 90, let's write them here. So this guy is 90 degrees minus theta over 2. And the same goes for this one, right? 90 minus theta over 2. So both of them are. In fact, I don't need to write this. It's obvious. Okay. All right. So this implies, if we look around, that the angle DCE, so the measure of the angle DCE, DC and E, right? This angle right here, this guy here, is nothing else than just theta over 2, right? Okay. Okay, so that, so now let's look at in this triangle CDE. Let's look at it. We want to look at it very carefully because we can get some information about this triangle. So we know that one of the angles is theta, the other one is theta over 2. Well, guess what? We can, since we know something about the angles, and there's also some information, so the angle is, this guy is theta over 2. All right. So I know that in this triangle, well, now consider triangle CDE. All right. I'm looking at this triangle right now. And what do we know? We know the two of the angles, and maybe we can get some information about the ratio of the side lengths of this triangle. Can we do that? Well, we have a theorem which gives us some information about this. Remember the sine law? We apply the sine law. Let me remind you, the sine law says that in a triangle, says that A over sine of A is the same as B over sine of B, and is the same as C over sine of C. And moreover, it's 2 times the circumradius. So I gave this in the previous lecture. Okay, so let's apply this in this triangle, and let's see. Guess what? Well, dE over, so we have dE over sine of theta over 2 is the same as CE as over sine of theta, right? Or if you want, this will be equivalent or equivalently CE over DE will be equal to sine of theta over sine of theta over 2. Okay. All right. So we have some information. Well, we're still not at EF. I'm trying to get something about that, but we'll get there. Now, the question is, can we say something? Keep in mind that we're interested in this guy here. At the limit as theta approaches 0 of the side length of the segment EF. We need to evaluate that. Okay, till then, can we get some information about the limit of this guy? Well, let's see. Remember, there is something. Remember that from Calc 1, the limit as a theta approaches 0 of sine of theta over theta, this is 1. Keep that in mind. This is a very important limit. It's one of the most important trigonometric limits, and it's usually taught in Calc 1, right? It's one of the most important. So now let's evaluate. The limit as theta approaches 0 of sine of theta over sine of theta over 2. And this guy here will give me, let's write it in this way, will be lim as theta goes to 0 of sine of theta over theta over sine of theta over 2 over theta over 2. And I forgot here, 2, right? And this guy will be nothing else than just keep in mind that this guy will, the limit of this will be 1, and also the limit of this as theta goes to 0 will be 1, right? So this guy will be 2. Which means that the lim as theta goes to 0 of this ratio CE over DE is 2. That's great. Now let's go back to the picture. So let's retain this information. And now let's go back to the picture. So I know that the limit of CE over DE is 2 as theta approaches 0. Okay, but I still need to find some information about EF. So I need to look about in another triangle. And now let me look in this triangle. In fact, let me look here. Here, E, B, and D. Okay, so let's look at the angle EBD, right? I want to look at this angle. What can I say about this angle? Well, guess what? This is, if you look here again, you see this triangle EFEB is the right angle triangle and has the right angle at E. So you can say something about this. And now let's see, let's look at this angle. So the angle EBD okay, will be 90 degrees minus the theta over 2 again, right? okay? And yeah, EBD. And also we want to look at this angle as well, EDB. Well, again, this angle yes, it will be theta minus, right? Anyway, so this is, so, and the angle EDB will be, again, EDB will be again, the same 90 degrees minus theta over 2. So these two, actually, I have made a mistake here. This is 90 over minus theta, not, okay, because I have it, wait, let me look. So it's 90, okay, that's theta. Yeah, it's 90 minus theta, okay. That was odd. So this guy will be in, okay, now we got the picture right. So the angle EBD is 90 degrees minus theta, and EDB is 90 degrees minus theta over 2. Okay, now we should compute the ratio, and you will see, okay, now I will look at DE, at this ratio, DE over E over, let me see, DE over DB, yes, over DB, and this will be what? Will be, again, will be this time, again, if we apply the sine law and everything, you'll get, so, okay, let me be more specific. Applying the sine law in triangle DEB, we have, and I'm just going to write it directly so that you wouldn't, so we have sine of this angle, so you'll have DE over angle, so DE over the angle EBD over sine of that equals EB over the angle EDB over sine of this angle, but sine of 90 degrees will give you cosine, so I'm just going to write it directly. So we will get DE, I'm just going to over EB, so this will be cosine of 9, so this will be cosine of theta over cosine of theta over 2. So we get this ratio. Well, and guess what? I'm going to do the same thing. This guy, in fact, I'll leave it to you as an exercise to show that as theta goes to 0, this guy will approach what? So cosine of theta over theta will approach something. So this will approach 1. And I'll leave it to you as an exercise to show this. This is, again, it's a Calc 1 problem. All right, so let's retain also this information. So let's keep this one here. So, okay, this one here, that the limit as theta goes to 0 of C of this ratio is 2. Now we have that the limit as theta goes to 0, because we're interested in this, of DE over EB is 1. And let's keep this information also. So we have these two so far. Okay, that's great. Now, now we want to see something about EF, right? It was still not there, but we're getting close. maybe we can get some information about this ratio, EB over CE. Yeah. So now let's see. So this implies that let's see. This implies that let's look at the picture again. CE, or yeah, well, EB over CE. And this guy, CE over EB, well, guess what? If you divide these two limits, right? Because by taking the ratio of the two, this implies what? That the limit as theta goes to 0 of CE over EB is what? Will be CE, yeah, will be 2. Or if you want to write the other way around, the lim as theta goes to 0 of EB over CE is 1/2. Anyway, so we have this. But also, what does this imply? It follows that that the limit as theta goes to 0 of what? Of let's look at the picture of EB over BC now, right? EB over BC. Well, it's easy to see this one because we know that, well, you know what happens. You can always write BC as EB plus CE, and you know what happens with the ratio of this. So I'll leave it to you. It will follow that. This would be 1/3. And I'll leave it to you as an exercise to check this. Okay. And now, now let's see what happens to the ratio here. We want to write a EF over AC is what? Well, let's look at the, okay, but now we have that, okay, let's look at the picture. You see these two triangles here? You will look at these two triangles, ABC, right? And BEF, they're similar. So therefore, this implies that EF over AC. Now the triangles ABC is similar to the triangle, this one here, BEF. So this implies that that EF over AC is the same as EB over EB over BC, right? Okay. So this means what? This implies that, so by taking the limit, so as theta approaches 0, we know that this is, we have that lim of EF will be AC times lim as theta goes to 0 of EB over BC, but that's 1/3, so it will be, so this guy is 1/3, so this would be AC over 3, and that's the end of the problem. Well, it was just this is basic geometry, like, so that's it. Anyway, I would like to say a few words about the official solution. The official solutions, well, this is a little bit more, this is how I did it. It's a little bit more complicated. I did it by hand. But the official solution has a trick, actually. Well, I'm not gonna go into the official solution. Well, and I forgot to say it's AC over 3, but this is AC is 1, so it's 1/3. Okay, forgot to say this. So it's 1/3. That's the limit. Anyway, the official solution is the following. So the idea is to reflect okay. Well, it's actually, well, if you have this idea, it's actually easier. Well, the idea is the following. So we reflect the point C. So we reflect C about the line AB, right? And then we'll get another point. And now we just do some angle chasing, and at some point you'll get something like. Anyway, this EF, when you compute it and you write, actually this is an angle chasing, you will get that this the length of EF will be nothing else than just sine of theta over 2 over sine of 3 theta over 2 anyway, and then you can just apply L'Hopital or whatever. Well, anyway, that was this is the official solution. It's, well, okay. That was the problem that I wanted to do. It's a nice problem. It has many ingredients here. You can use the sine law. You can use some angle chasing. You also use similarity. You also use some limits about trigonometric functions. It has many ingredients. And basically, you can just, the only thing you need to use here was just Calc 1 material, nothing else. All right, so that was problem number 4. Now let's see problem number 5. There was another problem that I wanted to do. Okay, and again, this was again a Putnam A1 in 1997. Again, it's these are considered to be the easy problems, but as you can see there, you need to be very careful with these easy problems. And the problem says the following: a rectangle let's say HOMF, right, has sides. Again, this is it's a similar problem in the sense that you need to draw the picture so that you can see it better. But anyway, let's state it first. So this rectangle HOMF has sides HO equals 11 and OM equals 5. A triangle ABC has H as the intersection, and also this is a big information at this point, of the altitudes. O is the center of the circumscribed circle. Again, this is another big information. And the midpoint of BC, okay, and F, oh my, and F, the foot of the altitude from A. The question is, what is the length of BC? The length of BC, that is the question. Again, like I said, it's a kind of similar problem with the okay. Now let's look at this carefully, and let's read the statement very, very carefully. And I think if we draw a picture, I think things will become even clearer. Okay. So let's see. So I have some information here that I want you to look at. Let me look. A triangle, look here. This is a huge information. We have said that the altitudes of a triangle meet at a single point, that their common point is called the orthocenter of that. So that is H. Also, we have another information that O is the center of the circumscribed circle. Again, another big information. And we will see that something happens. Maybe I could come up with another point here. So that is a trick. So the thing is that you need to have in mind the Euler's line, which says the following, that the orthocenter, the centroid, and the circumcenter, right? We only have here in this problem, if you look at the statement, we have the orthocenter, we have the circumcenter, but the centroid is missing. So maybe we should consider it, because I know from the Euler line that these three are on a line. So they're collinear. All right, but before that, let me draw the picture and then we'll talk about everything. Okay, here we go. So let's read the statement. I have a rectangle. Okay, let's draw the rectangle first. Ooch. So the rectangle is here, right? So this is, so these are the vertices, and let's call this H, O, H, O, M, F. All right, beautiful. So I have this rectangle. I know that HO is 11. And I know that OM is 5. Automatically, these two are 11 and 5. These are right angled here, all of them. Let's keep that in mind. Okay. Now a triangle ABC has H as the intersection of, okay, so I have a triangle ABC, so this will be the altitude. Let's say here it's, let's say this is B, this is A, and let's draw, ouch, draw it carefully. Right? Okay, and now this will be, now let's look at the, so I have a triangle ABC, H is orthocenter, and O, it will be the circumcenter, all right. Okay, let me draw it like this. Okay, this is my point C. This is how it will look like. So this is O here. So this is the triangle ABC. Great. And F is the foot of the altitude of the, okay, that's beautiful. M is the midpoint of BC. Oh, okay, wow. So these two are equal here. So BM, this guy here, is the same as this guy here. Okay, that's great. So these is the same as these. So let's keep that in mind. And let's see, what other information do we have? What is the length of BC? So we need to find BC. That is the question. So we need to find this entire thing. That is the question I want to. Okay, so now let's look at the picture very, very carefully. And so we have this. So you see, this is, so H, let's call this straight from the, so H is the orthocenter of the triangle ABC, and O is the circumcenter of the triangle ABC. And now look here, I have the midpoint. M is the midpoint of BC. This is a big information. If we draw the line here, let's just say I'm drawing AM. So M is the midpoint of BC. AM is the median of this. Well, at some point, they will meet. If we draw all the medians here, there will be a point G here somewhere. So this guy G will be the centroid of the triangle ABC, right? M is the midpoint of BC, so if I unite, if I have this line segment AM, this will be nothing else than just the median from A. Great. And on the median of A and the intersection of all medians, they meet at this one point, and that point is the centroid of the triangle. Great. So let's consider this. And moreover, we know one thing. Euler's line says the following, and we said this in the first lecture, that H, G, and O are collinear. They're basically on the same line. Right? So I know H, G, O are collinear, but keep in mind that I need to find the length of BC. So I only know some portions of this. And let's put some more information. This is a right angle triangle here, again here. I know FM, but I need to find MC, and I need to find BF, so that that is the question I need to do. Okay, now let's see. We have to analyze this picture a bit. Well, the problem is this in nature is similar to the previous one. It's not hard at all. In fact, this is the trick that the trick that we have to consider the centroid of the triangle, and we know that H, G, and O are on the same line. But moreover, this centroid has this property, and I would like to say it. So keep in mind that that G, that the centroid, let me write with, of a triangle, well, is, how should I say it? Lies, okay, I'm going to say it like this, 2/3, right, of the way from A to M. Right? Well, this also implies that the same thing will happen for H, but this H, if you look at the picture, will lie 2/3 from A to F, right? So this implies that that H, right, the orthocenter of the triangle, lies 2/3 of the way from A to F, right? Okay, okay. Well, what does this mean? This means that, can we compute AF? This is 2/3, right? We can compute this guy here. And if we look, it's what? Well, it's quite clear that it's 15, right? So let's write this. So the distance from AF is 15. So we're trying to get as many, to compute as many distance, as many length of all these lines as possible. So we have AF now. Now, let's look at, now, there is another thing that we need to observe here. And if you look closely, okay. So you see, we have this triangle here. Okay. Let's look at this triangle, because I'm trying to get some information. So let me look at B. So this triangle here, BFH. So again, this is a right angle triangle. So I know that FH is 5. Because I want to get some information about BF, right? Keep in mind that we're chasing this this line segment here, BC. We not want to find as many information as possible. I need to find something about BF. I need to find something about MC, and that's it. I can add them, everything. And so let's look. So I'm looking at this triangle, BFH is a right angle triangle. I don't know, maybe I could know some information about BH, right? BFH, and maybe I could do something. Let me look. So now the triangle. So we said, let me, BFH. And let me use a similarity again. This will be similar to what triangle? Well, if you can see, this is similar to this triangle, AFC. We look at this triangle, AFC, because I can get some information here. So these two triangles are similar. So AFC. So, okay, let me give some information. Why is this? In fact, I'm going to leave it to you as an exercise to see why they're similar. Okay, I'm just going to put it here, why, as a question mark. Well, it's quite clear that one information is clear. Both of them are right angle triangle. And also some angles are congruent here. But anyway, I'll let you figure this one out. And also by this similarity, this implies some ratio. So this implies what? This implies that BF over let's be careful here. BF. So BF over yeah, BF over. Okay, so this will imply that BF over FH will be the same as AF over FC, right? AF over FC. BF over FH is the same as AF over FC. Okay, that's great. So that's one information. Or let's multiply these two. So BF times FC is the same as AF times FH. Oh my. Okay. But this guy, AF or times FH, AF AF times FH, well, we know that AF is 15, so this is 15 times 5, which is 75. Okay, great. Great. So I have that the product of BF times FC is 75. Great. But now I can do something here. Let me look at BC squared. And I'm going to do a magic trick. BF times FC. Phew, that's great. You see, that's one thing. I have this product, BF times FC. Now, I know BC, I can write them as the sum, but BC is nothing else than just BF plus FC. And now let's square this. So this will be the square. So this would be BF squared plus FC squared plus 2BF times FC. I already know this guy here. This guy is 75. And now let's see. But maybe that's not the BF squared. Can we look BF squared? Oh my. BF squared. There is a problem here. What to do with these squares? Okay. All right. So there we can do something about it, but maybe that's not the right way to do. Well, we can write it in the following way, in the smarter way. And instead of writing in the bf squared, we can write it in the following way. We can write this as, okay, let me say it. Or even better, bc squared is the same as, so again, bf plus fc, everything squared. And now I'm going to do the following trick. So I'm going to write it in this way, bf minus fc, everything squared, plus, and now I'll have 4bf times fc. Okay, and now at this point, bf minus fc. So now we need to take care of this guy here. What about this guy? And let's look now. Let's look, bf minus fc, bf minus fc minus. And you see there, if you look at the picture, we can write this as bm plus, so you see you have 4 points. We have b, f, m, and c. So we can write it in terms of fm because I know that that's 11. So I can do this. And I know even one more thing. I know that bm is the same as mc. Keep that in mind. This is very important. So I can do this trick. Now bf minus fc, this will be bf. So I kept it, so this will be, let's say, bm plus mf. Okay, it's easy, right? Minus, and now I'll have mc minus mf. Anyway, that's easy to see. And now guess what? This will be nothing else than just 2mf, and I know that mf is 11, so this will be 22. Wow, finally. So this implies that bc squared will be nothing else than just, oh my, 22 squared plus 4 times 75, whatever this is. So bc is the square root of this guy. 22 squared plus 4 times 75, which will give me whatever, a number. 22 squared. Okay, it will give him an, in fact, I can do it with a calculator. Okay. Okay. So this would be the square root of, so 22. Okay, so 22 squared, this will plus 4 times 75. This will be the square root of 784. Ah, this is a perfect square. Wow, that's nice. 28. Okay, I'm done with this. I feel like I was in not even high school, in kindergarten, solving these kind of problems. Yeah. Whew, anyway. It was quite a chasing here, like not quite angle chasing, but segment chasing, line chasing, whatever. But I wanted to do this problem as well, although it's, I won't say it's, I prefer to spend time doing these kind of problems, but at least you can see some of these examples. This was a good problem for line chasing. You can see, you get some information about this. The previous problem was with angle chasing, and you got to use some of the sine law and so on, but this one was using line. Anyway, this was a nice problem. Now I'm going to do another one, and I'm going to stop with um, doing problems with from Euclidean geometry. I'd like to do some vectors as well. All right, now we're going to do problem 6. This is a bit difficult, but it's a much nicer problem. Well, problem 6 was in fact a Putnam A6. In what year was this? Problem A6 in 1998. Anyway, all right. So the problem says the following. And this is a very nice problem. It says that let ABC denote distinct points. So these are lattice points basically with integer coordinates. R2. Prove that if the following inequality holds: if AB squared plus BC squared, in fact, no, sorry, I'm wrong here. So it's AB plus BC, everything squared, is less than A times the area of the triangle ABC plus 1. Oh, that's a condition. Then ABC are 3 vertices okay, of a square. Wow. Okay, let's look at the problem. So this is a statement. The statement is a bit tricky, I would say. It's much more, it's trickier than the problem actually. So these means that, well, guess what? What do we have to prove? So let's analyze this. So these are the 3 vertices of a square. So this means that if we prove that AB is the same as BC, and if we prove that the angle between them is pi over 2, then, well, I guess that's it. How do we approach this? And also we have this important information that these ABC are lattice points. So let's say this. Keep in mind that ABC are lattice points. In other words, these are points of with their coordinates integer numbers. So that's what we have to prove. So maybe, well, let's think. You see, we have this weird condition here that this happens, that this sum of these squares is strictly less than that A times that area. So we have this inequality. So let's see. Let's draw the triangle. I'm going to draw it like this already. Right, and we have to show this, that AB. So keep in mind that we have to show that AB is equal to BC, and this angle theta, let's call this theta, is 90 degrees. So we have to show that. We should be careful here. Well, if you look at the condition, you'll be tempted to say maybe there are some inequalities, some geometric inequalities involved, or maybe something even simpler than that. And well, in fact, that's the case, but we have to be careful a bit here. You see, let's analyze this a bit. I have to prove, I have to show this, I have to show this. But I also have an information about the area of this guy. And I know the vertices are lattice points. And we have a following fact. I'm going to write it with red. And I think you can realize this, how you can prove it, is that the area of a triangle the area of a triangle, how should I, with vertices of integer coordinates well, the area of this is half of an integer, is half of an integer. That's very important. And well, the proof is not hard. You can just, well, you can pick one of, in fact, I'll leave it to you as an exercise. It's just basically calculus 1. But let me tell you the idea. So basically, you pick one of the vertices to be the origin, let's say, and then the others will be, let's say, P, Q, and RS, right? Whatever. And now you can the area will be the absolute value of something over 2, which is an integer over 2. Anyway, now let's. So we know this. So this guy, the area is half an integer over 2. Oh, it's a half an integer, right? And now I can also compute the area using well, whatever. Anyway, there are plenty of ways of doing this. I'm just gonna avoid the official solution is a little bit tedious, so I don't want to do that. I'm just going to do it my way. All right, let's look. So I'm going to start with the trick directly. Let's look on the left-hand side. You see this guy here? Okay, great. Maybe we can do something about this guy. And well, let's look. This guy here, let's expand this guy. So AB plus BC, everything squared. This is nothing else than just AB squared plus BC squared plus 2 times AB times BC. Okay, great. But now I can do the following. I know that this guy here is greater or equal than 2 times AB times BC, right? Keep in mind that that's the first inequality that we did, and I think it was in lecture 1, right? Let me remind you, this was here we apply that alpha squared plus beta squared is greater or equal than 2 alpha beta. That was just, this is a, you can just complete the squares or you just apply the AMGM. We did this in lecture 1, the very, very beginning of lecture 1. So we have this. Okay, and now also this guy 2 times A, okay, so this guy, okay, let me write it in, okay, maybe I should. Okay, let me rephrase it a bit. So we have this expansion here. That's clear. Also, let's keep in mind that AB squared plus BC squared is greater or equal than 2AB times BC. Again, this is what we said at the beginning, alpha squared plus beta squared is greater or equal than 2 alpha beta, which follows from AMGM or whatever you want. So that's one thing. And also, we also have that this AB times BC, this will be greater or equal than 2 times the area of the triangle ABC. Well, what is this? In other words, this is just well, you can use here law of sine law. Right? Or and also you use the fact that sine law plus this fact here, plus the, let's call this fact, plus the fact above. So these are the two inequalities that we need to take into account. So let's, this one, which follows by AMGM, and this one, which follows by sine law and the fact. Okay, so let's keep this in mind. Also, we need to, when we look at this, keep in mind that since these 3 vertices are on a lattice, this means that all these distances that you see there, AB squared, BC squared, and so on, these are integers, positive integers, okay. Well, let's see now. And now let's explore our inequality. Because we want to use these two. Now we have. So we want to use these two inequalities here. And we have, and let's explore our conditions. So AB plus BC squared So we have the following. Let me start. I'm going to do it like this. 8 times the area of the triangle ABC. This guy is nothing else than just, well, it's less or equal than, well, so I know that so let me split this into, so this will be less or equal than 8. So I'm going to use the second inequality, AB times BC. But this guy, I'm going to split it into, or actually, no, let me do it like this so that it's clearer. So this will be, so now let me use the first and the second inequality, right? So this will be less than AB squared plus BC squared plus 4 times the area of the triangle ABC, right? If you look at this inequality, I've used, so 4 times the, it's less than 4ABC, which will be, well, right? I use the second inequality and the first inequality. Let me call this, this is star, and this is double star. So here I use both star and double star. Okay, and now guess what? I'm gonna use it again. This will be less or equal than, and now I'm gonna use the double star inequality. So this will be less or equal than what? Then AB squared plus BC squared. Okay. Okay, and now this will be less or equal. So here I use star, double star, sorry. So here I use double star. So this will be less or equal than AB squared plus BC squared plus 4 times 2 times plus 2 AB times BC. Okay, beautiful. But this guy is nothing else than just, as we know, AB plus BC, oh, sorry, everything squared. Right? And now guess what? Now we're going to use the condition. We know that this is less than, which is less than 8 times the area of the triangle ABC plus 1. So we started, so what does this imply? Note that this guy here, let's keep that in mind, that this guy, we started from, this is an integer, but this guy is also an integer. Well, what do we can conclude now? Well, this means that, well, the this means that means what? Well, it means that we'll have somewhere equality here. So it will imply that 8 times the area of the triangle ABC will be equal to this guy. So it will be equal to AB squared plus BC squared plus 4 times the area of the triangle ABC. Okay, so so 4 times the area of the triangle ABC is equal to AB squared plus BC squared. Okay, great. But also we will have, so we'll have equality here. So this will be also 2 times AB times BC. In other words, we'll have equality and AMGM inequality, but both of this will imply the fact that AB is the same as BC, and moreover, that since the area and since 2 times the area, okay, let me write it here. 2 times the area of the triangle ABC is AB times BC, right? This will imply that the angle B is 90 degrees. And that's exactly what we wanted to prove. And that's the problem. Anyway, I think this sums up the lecture today. Next lecture, I will continue again with geometry. So I'll have a geometry lecture where I'll be talking about vectors and maybe a little bit of complex numbers and coordinate geometry. Anyway, some analytic geometry, we'll see. I think this is a good place to stop here. Thank you very much.